Not outside, but
Still taking some time. Okay, yes, we are live. Okay, I welcome all of you for this edition of the NSF Wednesday Colloquium. And it's a pleasure to have one of our own colleagues from the Department of Theoretical Physics, Professor Amol Dighe, talk about the anomalous magnetic moment of muon. So before I actually formally introduce and welcome Professor Dighe, as we fondly call him Amol, I would like to give a little bit of a brief history of about the NSF Wednesday Colloquium. The Wednesday Colloquium actually is as old as TIFR itself and was started by Professor Homi Bhabha, the founding director of the institute. And the idea was to bring together all the three sort of subfields of science, physics, chemistry, and biology, the scholars from all these three subfields in the institute, to sit together on a Wednesday afternoon and listen to experts who would be visiting TIFR and sort of experts who could talk about the science in a broad perspective, give a colloquium and discuss with the experts and amongst the various institute members, and have spur ideas of collaboration as well as other just scientific discussion. This has been a very rich tradition of TIFR and has actually caused a lot of interaction within the various departments in the institute. So it was a brilliant idea, and it has been carried over for all these years in the institute. We have been fortunate enough to have speakers from the institute itself, because the institute boasts of world leaders, and today's speaker is no different. We have Professor Amol Dighe, who actually is a professor in the Department of Theoretical Physics, with a strong interest in understanding high energy physics with focus on neutrinos, particles like neutrinos, their nature and the role they play in astrophysics and cosmology. Amol got his bachelor's degree from Indian Institute of Technology, Bombay, and did his master's and PhD from University of Chicago. He moved to ICTP and CERN and Max Planck Institute to do his postdoctoral work. And in 2003, he joined the institute. Within 10 years of his joining the institute, he was awarded the Shanti Swarup Bhatnagar Prize for his incredible contributions in high energy physics. Amol, without further ado, I welcome you to talk about the latest experiments from the Fermi Lab that actually measured the magnetic moment of a muon to very high accuracy, and how it does not match up with the theoretical predictions. So, Amol, the floor is all yours.
So thanks, Jyotishman, for that nice introduction. So as you see from the original slide, the title slide, this is going to be a conflict or confrontation between the measurement from the instrument that is to the left-hand side. We will come to that in detail in the later part of the talk, and the calculations that you see on the right-hand side, about which we will talk in the perhaps first half of the talk. So all of this, of course, came because very recently, to be precise, exactly 3 months ago, I think on 7th of April, the Fermi Lab experiment called muon G-2 declared its measurement of the so-called anomalous magnetic moment of the muon, and we will see what this means in a short while. So to those of you who want an executive summary, that's what this is. So on the confrontation, the measurement is the measurement of the gyromagnetic ratio of the muon. The experimental value of G mu, as you see on top, looks something like this, and I'm not even going to bother reading all the numbers. The theory prediction is given on line number 2. And now if you try matching those sort of decimal point by decimal point, you will see that I think 2.00233318, they are the same, and afterward you start having seeing some differences. The way people describe errors on these quantities are like this. So these 8 2 into bracket means that these are the errors in this whole quantity. So it means instead of in the last digits 2 2, the error is of 8 2. Okay, so which means that the error is basically in the last 3 digits. If you want to look at what is the significance of this and subtract the 2, you get the value of delta G mu to be about 500 plus or minus of 100 or so times 10 power minus 11. The quantity which is most often quoted is not G mu, but the quantity called as the anomalous magnetic moment, which is A mu, which is G minus 2 divided by 2. And just a visual representation here would look like this. So the standard model prediction is something like this vertical green band. The prediction of the new Fermilab result is this red dot with error bars. There's an earlier experiment from Rukeman lab whose measurement is given by blue, and the average of these two is given by this purple band. And these two bands differ by 4.2 sigma, which basically is the same as the number you see above, 502 plus minus 118 times 10 to the minus 1. So well, so this is in some sense the final slide. So those of you who wanted to just hear this can in fact now go home. But let me talk about this because this was a thing of interest for me. I must be clear and tell you that neither have I worked with the experiment, nor have I done the theoretical calculations. Okay, so I'm talking about this because I find these results interesting and exciting to talk about. Okay, so in fact, whatever you will see in this mostly comes from the following references. This was the paper from the muon G-2 collaborations that came out on 7th April 2021. I will also talk about this second paper, which is a so-called white paper or the theory initiative paper, where a lot of theorists doing calculations of this quantity came together last year and published this. And very recently, there have been some very nice talks. The talks by Aida El Khadra and Chris Polly were the ones which were given when the announcement was made. And then in the last 2 months or so, John Ellis and Massimo Passera, two of the people who were involved at some level in the calculations, actually gave some very nice talks at the respective places I have talked about. Okay, so I must thank all these people also to sort of get me interested and also clear my doubts. Okay, so let's start from very basics because after all this is a colloquium.
Can I ask a quick question, Amol?
Sure, sure.
Yes, you can immediately start. I just wanted to, because the numbers you showed in the second slide, and you showed a deviation in the sixth place or seventh place, I don't remember. So you will talk about the manifestation of that deviation in terms of how off we will be in our predictions in some of the aspects.
I will.
Okay, fine.
And Amol, this TP here.
Yeah.
What about the other theory paper which came in Nature the same day as?
Maybe after 55 minutes.
Ah, okay.
Yeah.
Okay, thank you. Thank you.
I will come to that, yes.
Thank you.
Okay, so let's start from very basics. Okay, so this is about magnetic moment. So in some sense, this is about understanding what a magnet is. Normally, of course, what you see and think of magnet is what you see on the top. But we know that this has, we understand it in more detail now. We understand how a magnet works in terms of classical theory of electromagnetism, where magnetism can be produced by a current carrying wire. We understand this in terms of quantum mechanics, when you have spin, and spin, of course, will give you something about magnetic moment. And what is very important for the anomalous part of magnetic moment is quantum field theory, where we know that the vacuum that we see is not simple vacuum, but particles keep on getting created and destroyed. Okay. So first, a simple magnetic moment. If you have never heard of this, which I really doubt, This is basically just the strength of a magnet. Okay? So the magnetic field produced by a simple magnet, which have north and south poles, essentially is extremely similar to the magnetic field by a current carrying loop. And in fact, if you are far away from this loop or from this magnet, it will be impossible for you to figure out if the magnetic field that you see came from original sort of north-south pole magnet or whether it came from a current carrying loop. Okay, so we know that electricity and magnetism are just two sides of the same coin. So now we go a step further and we try to relate the angular momentum of electron going around in the loop with the magnetic field that it creates, the magnetic moment that it has. So this is electron going around in a circle with velocity v. So clearly its orbital angular momentum is m r cross v, and it will be upwards in the direction of L that we showed. We can also calculate the magnetic moment of this, or magnetic dipole moment as we call it, as half of r cross j, or in simple terms, because it's a simple one electron, it is just half of q r cross v. And if you compare this L and mu, you notice that, well, they seem to be very easily related. They are related as mu equal to q upon 2m times L. And you suddenly find this g coming into picture. Value of g is 1, so right now at this point it means nothing. So question will be, why do I bring this g at all? And the answer perhaps would come in the next 5 minutes. So why is magnetic moment defined like this? The original meaning of magnetic moment is defined by its interaction with the magnetic field. So what happens? If something has a magnetic moment mu and it is kept inside a constant magnetic field B, then the torque on this object is tau, which is mu cross B. And as a result of this torque, the magnetic moment precesses about this external magnetic field B. And the frequency of precession, as we know, is called the Larmor frequency. And in the at least non-relativistic limit, the frequency is given by GQ upon 2m times P. So now you see, this actually gives us a way of measuring magnetic moment. Okay? So you put the magnetic moment in an external magnetic field and measure the value of Larmor frequency, and therefore you can measure the value of G or the value of mu. Okay? So now this is a straightforward thing for us. Okay, all of this was classical, and we looked at electron going around in a circle. In 1922, there was the so-called, the famous Stern-Gerlach experiment, in which he had a beam of silver atoms, which were passed to inhomogeneous magnetic field, and whatever deviation they underwent was seen on the screen. Now, suppose these silver atoms, or the electrons in the outermost shell of the silver atoms, did not have magnetic moment, then they would not get affected by this magnetic field, and this beam would simply come straight and hit the screen. You would get one simple blob. Suppose these electrons had a magnetic moment, then depending on the direction of this magnetic moment, because that would be quite random since electrons came out of a furnace, you would get a band, because depending on how much is the magnetic moment, the direction of magnetic moment, it would get deviated to a different extent. However, as is well known, what they observed was not continuous pattern like this, but simply two big blobs. So this told us, firstly, that electron has an intrinsic magnetic moment because something deviated. So there must be something which interacted with the magnetic field. But secondly, it also told us that this magnetic moment is quantized. Not only quantized, it can take only two values. So now we are in the domain of quantum mechanics, where the magnetic moment takes discrete values. With this, we can try to talk about the value of G in the case of spin. So what have we seen? We saw that the magnetic moment was quantized, and this tells us that the angular momentum that electron may possess should also be quantized. We saw that this angular momentum had two discrete values, and we know that when J angular momentum has two discrete values, it means that their Z component has to be plus or minus h cross by 2. Okay? So we now know that electrons spin angular momentum is plus or minus h cross by 2. Experiments were done to actually measure the value of this magnetic moment, and which comes from the measurements of Zeeman effect. That gives you the value of magnetic moment as E h cross by 2. Okay, so now just like we had a magnetic moment and angular momentum in the case of electron going around in the circle, we can do the same thing here also. And here we find that mu z is 2 times E by 2m times S. So instead of that 1, G equal to 1 that we saw earlier, now we suddenly have G equal to 2. Okay? So this means that for spin angular momentum, the gyro magnetic ratio of an electron is G equal to 2. And in fact, it is the same for all spin angular momentum. Okay. This is a slide that's kind of a fun slide. I like to show it simply because I like this. Talking about electron spin. So it is often explained as imagine a ball that's rotating, except it's not a ball and it's not rotating. Okay, so that's
Amol, sorry, quick question. In EPR spectroscopy, you detect these G values typically. So for a free electron, it's slightly more than 2, which is 2.0025. But that correction comes from what then?
Yes, maybe 10 more minutes.
Okay, fine.
This is what I'm leading to. This is in fact the anomalous magnetic moment of the electron.
Sure.
Yeah?
Okay.
And you will compare. Yeah, thanks. So I'm sure so people have heard of it. Good. So just a few things to have at the back of our mind, even though we perhaps know it by heart. So spin is a purely quantum concept. You cannot imagine this as electron rotating. It has no analog in classical physics. Mathematically, it behaves exactly like angular momentum. Okay? And it gives rise to a magnetic moment with G equal to 2. So the postulate that electron has spin actually was proposed first by, if I'm correct, Goudsmit and Uhlenbeck in 1925. And very recently, I read the transcript of a talk by Goudsmit. And he explains that how he came to this idea by looking at the Zeeman splittings. And at some point of time, so he said, I didn't want to do calculations. He just because of the degeneracy, he said that there must be, the spin must be half. But at some point of time, he went and met Heisenberg. And Heisenberg asked him, what have you done with the factor of 2? And neither Goudsmit nor Uhlenbeck had even thought to do this calculation and figure out a factor of 2. But that is when it was realized that the German magnetic ratio, if you have a spin, is actually 2 and not 1. So this is a very interesting talk that one might go to web and try to read. Then came Dirac, and in relativistic quantum mechanics, Dirac explained why G should be equal to 2 very beautifully. Okay? And it came out almost naturally. So what did Dirac say? Dirac actually told us what electron means. Okay? So Dirac told us that electrons are described by the solutions of the Dirac wave equation, okay, with potential A mu, which is given by whatever, phi by c times phi by c and A. This is the A mu 4 vector. And what you see here is the Dirac equation. Okay, so if you have seen this earlier, of course, you will immediately recognize this. If you haven't seen this, don't worry, this is what the equation looks like. Now, this equation tells us two very important predictions. Prediction number 1 simply comes from nature of the equation. The solution of this equation is what is called as the spinor, which is a 4-component vector, 4-component object, I should say. That is because this gamma mu, called as Dirac matrices, are 4 by 4 matrices. And these 4 components actually tell you that the spin of the object has to be equal to plus or minus h cross by 2. So the fact that electron has a spin of h cross by 2 comes naturally by saying that electron satisfies Dirac equation. Second thing we get from this is we could actually, using this Dirac equation, calculate the magnetic moment of the electron. by looking at its interaction with magnetic field, which is del cross A. A is already in this A mu. And once you do the calculation, you will get G equal to 2. So lesson after all of this is that in relativistic quantum mechanics, the value of G is simply exactly equal to 2. Okay. So the question is, where does G minus 2 come from? And that's going to be the next part of it. So this comes from quantum field theory. The quantum field theory gives us a different way of looking at the world around us. It tells us that all the particles that we see are actually quantum fluctuations in fields. Okay, so there's a field of all particles and all we see are quantum fluctuations. The real particles are the ones that we can observe directly. However, even in the vacuum, virtual particles keep on getting created and destroyed as long as they last for a very short time. Okay? And approximately is given by uncertainty principle. If the energy is high or the mass is high, they will last for a short time. This is, of course, a very vague way of looking at it, but mathematically, I can assure you that this can be concretely stated what it is. That gives you the picture that I showed you earlier, that in vacuum, you have got particles going back and forth, getting created and destroyed. While they do this, these virtual particles can interact with real particles. They can get emitted or absorbed. And that is, in fact, what gives us deviation from G equal to 2. So let's see something very basic about this. You can see perhaps this animation. The time goes from bottom to top. What the animation shows is 2 electrons that start coming from the bottom. You will notice that the left electron, after some time, will emit a photon. This will be that virtual photon being emitted, which will not be observed. But this photon will be absorbed by the second electron, and therefore electrons will interact. So once we had this theory, this prediction of QFT, that particles can be emitted or absorbed from real particles, then we understand why electrons interact with each other. And this is what is called as QED or quantum electrodynamics. Okay? So these are Feynman diagrams. We'll come to them very often. In the rest of the talk, in my Feynman diagrams, time will go from left to right. Okay, this is just to make sure. So what we right now saw, the one part of it could be this electron. So this electron, which is going from left to right, interacts with a photon. This is what is called a tree diagram. And if you calculate this tree diagram, it gives you G equal to 2. So G of E stands for G of electron. Okay? So again, I'm not going to show this. Take it from me that if you calculate this diagram, you exactly get the value of G equal to 2. However, QFT told us something more. It told us that in principle, particles can get emitted and absorbed, which means that in principle, this electron, before interacting with this outside external photon, can actually emit another photon and absorb it after some time. So in addition to the upper diagram, you also get the second diagram. There are ways of calculating this diagram, and this calculation gives you correction to the value of G. And this correction is calculated, and this turns out to be alpha by pi, which is about 1 by 137 pi. Alpha is the famous fine structure constant. So this is what gives you corrections to value of G, and that tells you that G cannot be equal to 2, has to be different from 2. But that's not all. Because once I open up this avenue, why only photon? I have the whole standard model. Standard model of particle physics has many particles. It has quarks, leptons, gauge bosons, Higgs boson, and so on and so forth. All these particles can be created as virtual particles, and all of these particles can interact with that electron. So which means that if I want to calculate the value of the magnetic moment, I have to calculate the effect of all these particles. So the Dirac term, then from electrodynamics, where you exchange one photon, it could be exchange of Z boson or W boson with a neutrino. It can also, so this has electromagnetic and weak interactions, but it can also have strong interactions, because you see a photon also interacts with quarks. which means that you can also have hadrons here. So this blob, yellow blob that you see, is because of the hadronic contribution, which also can be there. So only when I calculate all of these diagrams will I be able to predict the exact value of G. So this is a slide just to scare you a bit, saying that calculations are complicated. These are two loop diagrams, which you see will come on top of the one loop. There are four loop diagrams. Well, there are three loops also, four loops, five loops, and so on. And people actually do calculate. We don't want to calculate that, so we use a simple short form notation. We say that this left-hand diagram gives us G equal to 2, and this diagram, whatever happens here, is G minus 2. Okay, and that's the reason that the experiment also was called a G minus 2 experiment, because everybody knows about this 2 that was given by Dirac, and all you're interested in is the deviation from 2. Schwinger was the one to calculate the deviation for the first time, and this deviation, this A, which was G minus 2 upon 2, was alpha by 2 pi, which he calculated in 1947. Schwinger's tombstone actually has alpha by 2 pi on it, so it also shows that he was so much attached with this particular quantity, and of course that's one of his greatest contributions. The first measurement of this was done by Kush and Foley immediately after in 1948, and this actually came from atomic spectroscopy, as Jyotish just mentioned. After this, of course, people measured, people like Sommerfeld, Peterman, etc., measured the contributions to order alpha by pi square, and so on and so forth. Okay, this was about magnetic moment of electron. So people have till now calculated this magnetic moment of electron to about 5 loops in QED, plus a few loops in electroweak theory and also strong interactions. So this is the status of magnetic moment of electron, okay, not muon, just to be specific. So the value calculated looks like this. So this 1528 is the error on 3632. Just to reiterate, the measured value is this, and now you will notice that this quantity actually matches to, I think, 9 or 10 decimal places. So in fact, if you take into account the errors, it's about 12 decimal places the quantity has this measurement is done with a penning trap. You trap single electrons, look at the cyclotron frequency, and compare that with the spin precision. Okay, so that's the way to measure it. I will not go into that. I just wanted to mention that these two values, in a sense, match to about 12 significant figures. These three guys, Feynman, Schwinger, and Tomonaga, actually got a Nobel Prize in 1965 for the discovery of QED, or the theory of electromagnetism. Okay, so this is about electron, and now we are going to go to muon. So what is muon? Muon is, of course, electron's heavier brother. It was discovered and was produced in cosmic rays. It was discovered in the early 20th century, and Homi Bhabha was one of the first people who said that this is a heavy electron. Turns out that it's about 220 times heavier than an electron. At that time, many people thought that this actually was a meson, because Yukawa had predicted what were called as spy mesons, and when it was discovered, it was actually called as a new meson. Bhabha happened to be one of the first few people who said that this cannot be a meson because this has no strong interactions. It was too penetrating, and therefore it has to be more like an electron than a meson. Okay, so he actually called it heavy electron. Now, of course, we produce it not just in cosmic rays, but also at particle colliders, and we will use it extensively when I come to the experiment. Okay, so now, just like we used the anomalous magnetic moment of electron and its measurement to 12 decimal places as a precision test of standard model, or mainly the QED, now we want to use the muon magnetic moment also as a precision test of standard model, because it's possible that muons will be able to capture something that electrons could not. So let's now try to have a precision test of the standard model by measuring the anomalous magnetic moment of muon, which is G. So again, people calculate things. First one, of course, by Schwinger. This part does not change when you go to muon. Neither is the second part, which is again Sommerfeld and Peterman. They calculated it to order of alpha by pi squared. Kinoshita et al. Did in 1967 to cubic order, which means sort of 3 loops, then 4th loop and 5th loop. There are many other people, but Kinoshita is like a common person everywhere. I was not born in 1967. Okay, so this means that Kinoshita has been calculating the value of anomalous magnetic moment of muon since before I was born, and he is also one of the authors of this 3 initiative paper that came out last year. Okay, so which means that as long as I am alive, he has been calculating the value of G minus 2 to more and more precision. Okay, he really is one of the stalwarts in this area. So, electron, as you saw.
Question. Sorry to stop you.
Yeah.
What causes the muon magnetic moment calculation to be different from that for the electron, if at all there's a difference?
Yeah. So the calculation actually are very, so in the standard model, the calculation actually very, very similar. Okay. So the difference is not very large, except that I think electron, the corrections to electron dipole moment are suppressed by a value of, I think, me by mu squared as compared to the contribution to muon dipole moment. So therefore, if there is new physics, its contribution to muon dipole moment is expected to be about 40,000 times higher. So you expect to find new physics first in the muon dipole moment.
So the mass does enter one of the terms at some.
Yeah, so mass enters some of those.
Okay, thank you.
Not in the first order term, but I think it enters in the second order.
Okay, thank you. Thank you.
Okay, so measuring electron dipole moment was kind of simple. Of course, we saw atomic experiments can do that. Paging time experiments can do that because, of course, you have a lot of time to make those measurements. Muon is unstable. Its lifetime is only 2.2 microseconds. So therefore, it is, you have to measure it that quickly in some sense. So for all you know, it will decay before measuring its magnetic moment. So which means we have to do something extra. And of course, we have relativity which comes to our rescue to some extent. And relativity tells us that if the muon is traveling with a speed which is quite large, then although the lifetime of muon in its rest frame is 2.2 microseconds, its lifetime measured in lab actually increases by the factor of 1 over root of 1 minus b square by c square, which is the factor of gamma constant. So therefore, tau in lab frame could be more than tau, which is in the muon rest frame. So this means that if you want to design an experiment, this muon must be kept moving very, very fast. So let's try to design such an experiment, and the current sort of preferred way of doing the experiment is using a storage ring. So how does the experiment go? Protons are accelerated to high energies. They hit a target, like beryllium, for example. This target produces pions. Charged pions decay to muons, okay? And these muons, after collimating them and choosing them properly for the energy, you make them go inside a ring. So they keep on moving inside this ring. In this particular diagram, momentum is black arrow and spin is red arrow. Now what you do is you apply a uniform magnetic field B, which is perpendicular to the plane of this figure. So of course, then what will happen is that this mu will precess about the magnetic field. And therefore, the direction of momentum and the direction of spin will change. So the frequency of this precession will tell you about magnetic moment of muon. So final aim is to measure the frequency of this precession. Okay, things are slightly complicated because this happens only in a very particular case. This omega in the left hand side that you see is the frequency of precession. Well, it's all there also is axis, so this is omega A, called anomalous frequency of precession. It is given by this expression on the right hand side, and we look at it slightly carefully. The first term is the simple term that we already saw, which has anomalous magnetic moment A mu q upon n as magnetic field B. The second term has a v dot b term and has a complicated dependence on the velocity. So does the third term. So if you want to design an experiment which does not have these complications, you can do two things. One is that you ensure that the velocity of muons is always perpendicular to magnetic field, so that v dot b term is 0. In fact, the storage ring that I described some time back actually satisfies this. So second term goes to 0 and we are happy with this. The third term is complicated because it is not always possible to ensure that electric fields in this apparatus is 0, because you know that magnetic field and electric field are always connected to each other. However, what is possible to do is to choose the value of gamma in such a way that this big bracket actually vanishes. So this is called as the magic energy. At magic energy, the bracket vanishes, and that actually tells you that gamma is nearly 30, which means energy is about 3 G or 3.1 G. That's what tells you that in the experiment, if you want to make it a clean one, you need to use velocity perpendicular to magnetic field and energy very finely collimated to the value of about 3.1 G. So we have fixed the parameters, and which means that given magnetic field, we can find out radius of electron going, or the muon going around in the circle. So with a magnetic field of about 1.5 Tesla, radius of this circle is kind of manageable, is about 7 meters or so. So this expression therefore tells you why the experiment was constructed, such that with a reasonable magnetic field at a reasonable radius, we have a compromise of how to do the experiment. Now, so we found that we can, if we can measure the muon spin frequency, we will be able to determine the value of its magnetic moment. The question now is how to measure this frequency. How to measure the direction of spin. For that, you use some particle physics. You use the knowledge that if the muon spin is in the particular direction, when muon decays into electron and two neutrinos, preferentially, electron is emitted in the direction of the spin of this muon. There is a certain angular distribution which can be very well calculated, also because the energy of muon is fixed. Okay, so the positron, for example, is emitted preferentially in the direction of spin. So what you see here is a polar plot showing what is the probability of positron being emitted in a given direction if the muon is at this cusp that you see. So you will see that it most likely will go in the forward direction. Probability of it going in other directions is there, but it's very small. So experiments are going to be designed such that you are able to capture the positrons going in forward direction. You also use the fact that these positrons will have higher energy because they will be boosted in the direction of this muon. And that makes the removal of background much easier. So the principle of the experiment looks like this. So the muon enters from this left-hand side. The triangle that you see is the direction of its spin. Okay, just to emphasize it more. And you see this spin is going to precess about a normal to the plane of this slide that you see. Okay. Now, what you do is you have only a single detector, it is placed at this orange point that you see on the screen. It only detects electrons that are a decay product of the muon when the muon is at the extreme point of a trajectory. So this achieves two things. It achieves the fact that you ensure that you're only looking at muon when it decays at the extreme point and not when it decays at the other points. Okay? Because remember, muon is of course always decaying. But once you have this electron, if the spin of this muon was directed along, let's say, pointing towards left, the number of electrons that you see would be more. If, as you see in this figure, this arrow is not pointing towards left, the number of electrons that you see would be less. And you can imagine that as this arrow goes round and round, the number of electrons that are produced that you can see in the detector will go sort of up and down like a sinusoidal wave. And that's exactly the principle that this experiment is. So one thing you'll realize that this means that you need a very, very precise magnet. And in fact, the magnetic field inside this is measured very precisely. The method used is actually using NMR probes, which of course might also interest our chemist friends. Okay. People have started measuring this for a long time. The first measurement was done in 1957 by Lederman et al. With error that looked like this. CERN sort of took over from 1958, and you can see the decreasing value of errors on the experiments. So starting from error of about 0.4%, it then went to sort of 270 parts per million, 8 parts per million, and finally Bruckmann experiment gave the error to about 47 parts, 0.47 parts per million, okay, or 470 parts per million. All throughout these years, there has always been a tension between the theory calculation and experimental measurement. So this is not a new thing that there is a discrepancy. In this particular plot, the orange band that you see are experiments, and the purple or blue green band that you see are theory. So you will see that theory calculations, this is the top of this is around 1979. Okay, so around last more than 40 years. So you will see that all the theory bands that you see are here, which are bluish, and experimental bands also keep on decreasing quite drastically till you finally get this vertical band, which looks like beige or orange, depending on the screen color. All theory measurements seem to converge on one particular band. All experimental measurements seem to converge on one particular band. At some point of time here, you will see the theory predictions suddenly shifting with a small amount and moving towards right. You can see it around maybe 7th or 8th row from bottom. It actually has to do with the fact that at that point of time, an error of minus sign in the calculations of Kinoshita et al. Was discovered, well, by themselves, I guess, and therefore the central value of the prediction changed. So, however, the discrepancy still stays. So this was the stage before April 7, 2021. The difference was about 3.7 sigma. You notice that over a very long time, since 2006 onwards, theory predictions kept on getting updated, but experimentally, this result was the one that came after almost 15 years after the last measurement. Not surprising because it takes that time to actually build an experiment. So let's now go to what the experiment was. Yeah, is there a question?
Amol?
Yeah.
And you hear, so previous slide, this when this order change, third order to fourth order to fifth order calculation in theory calculation, when the transition happened? I think initially.
Can you be louder? Govinda, I cannot hear you well. Can you be a bit louder?
Oh, I'm saying that this calculation you showed initially, this is the first order, second order, third order up to fifth order. And here, is there anywhere you can say that this order transition occurred this year to that year? Is there any shift due to this calculation?
No. So remember, I can show you the times. I think the fifth order actually came in 1980. Sorry, in 1990. Sorry. Okay, maybe I will not go so much back. So even the fifth order came in 1990, which is the third line from the top. So that's why this error got reduced from the second line that you see on top to the third.
Okay. Okay, and then only the sign change is the main thing happened.
Then this was a sign change, and of course, people have been using better methods of calculating this. At the end of the talk, I will point out one particular process for which the calculation actually needs to be defined, and it's sort of the suspect process that needs to be calculated.
Amol, these are perturbative calculations, so you have to worry about the convergence and all that? Or?
Yes, so 10, maybe 15 more minutes.
Sure.
Yeah, so this is of course the right caveat. I will point out one particular contribution that has to be calculated non-perturbatively somehow, and that is, can people actually do the calculations? I will show the results very soon. Okay, let me quickly describe the experiment. So experiment is at Fermilab. This is the recycled ring where I guess you accelerate protons. Protons will come, hit this target, produce pions and muons. When you keep them circulating and collimate there in this delivery ring, and this MC1 is the room in which the experiment actually is done. Mu2E is a different experiment, and we will not go there. So this in this MC1, this is your detector. So the blue circle that you see is actually the same magnet that we talked about. The top of this, you can see this slightly reddish color. That is the beam line. That's where the muons come from. And then they start going round and round in this blue circle. Near the bottom, towards the left, is a detector, which will detect electrons that decay from muons that are decayed when they are somewhere around this point. I hope that you can see my cursor. This is the big hall. You can see this person standing here. We already saw that the radius of this ring is about 7 meters. So that gives you idea of how big the experiment is. Okay. So some details. So as you saw, as we saw earlier, this muon keeps on going around in this. Its spin starts precessing about its direction of or about its momentum. Energy is such that with each revolution around the ring, the spin axis rotates by about 12 degrees. So that's a reasonable number, and you can measure those oscillations well. It takes about a few hundred revolutions before the muon decays into electron and two neutrinos. So one bunch is actually let go around this ring for about few hundred revolutions. Okay. And then using some energy cut on the electrons to ensure that it is indeed coming from muons when it decayed at this extreme end, which is the bottommost on the slide.
Quick clarification, Amol.
Yeah.
So at the point you have the detector is the point where you you showed that polar diagram that muon, the electron coming out of the muon decays at some point it is maximum. So is this the point where we have, the detector is placed, right? I just want to be clear about that.
So detector of course fixed. Okay. Now look at the spin of this muon. Okay, this white arrow, for example. Okay. Suppose the white arrow was pointing towards left, you would get maximum number of electrons. When the white arrow has rotated, you will get slightly less number of electrons. When the white arrow points towards right, you will get minimum number of electrons. So as the white arrow rotates, number of electrons detected will go up and down.
So basically the detector position is it can be placed anywhere else, right? That is all. Okay.
It's just fixed once and for all. And you do not look at all the decays that happen throughout the ring. You only focus on this decay at this point.
Fine.
Yeah. Okay, so that's what the result looks like. Okay. So the result looks like these oscillations that you see. Now note that we said there will be oscillations. However, muons are decaying all the time. And therefore, the number of muons in the ring also keep on decreasing exponentially. So what you have is not a simple sinusoidal oscillations, but oscillations that actually decrease in magnitude. So you see the first row that keeps on going down like this. The way the plot is made is after you reach the right hand end, you come back to left hand end and you start the second row. So all the thing that you see is actually one continuous curve. It just, instead of having it on a long strip, you have folded it around so that it looks like this. Amazing thing is that the measurements start from 10 to the power 6 electrons every time bin. Time bin happens to be about 150 nanoseconds. From 10 power 6 all the way to 10 power 2. So the number of muons go down by a factor of 10,000, but still the curve is a perfect fit to the function, which basically looks like exponential decay e power minus t upon gamma times tau mu multiplied by 1 plus cosine function, distribution modulation. You can do Fourier transform of this, and you will notice that the maximum, this is actually the FFT spectrum, the fast Fourier transform spectrum. You will see that the maximum is at one particular frequency, which is actually the cyclotron frequency of this. But you also see some other frequency in this, which is what will give you the muon magnetic moment. Okay, so finally you have these results, right, which give you that it is about 4.2 sigma away from what the experiment average is. Okay, now that we have this, let me just tell you a sort of quick nice thing, because it's often something which is yeah, interesting stuff. So remember, we actually said that we need muons with a fixed energy, and we also would perhaps like magnetic field to be of the same order. Making a magnet to do this job is actually very difficult. As a result, the Fermilab experiment did not make a new magnet. They actually used the magnet which was used in the Brookhaven National Lab in the experiment that was conducted in 1990 to 2001. So these people also had shown deviations, which you already see here, and the Fermilab results actually are calculated, are actually measured using exactly the same magnet. Of course, one would say that this is no fun because you just got the same result using the same magnet. It is indeed only a preliminary result. It is expected that within the next couple of years, you will have about 15 times more data, which basically means the number of events goes up 16 times, errors go down by about 4 times, and therefore it is expected the error on this in about a few years will go down by a factor of 4. So that is what is expected. So this magnet actually had to be brought from Brookhaven to Fermilab, and however good your roads are, this is, remember, about 15 meters wide. Okay? So bringing it all the way is not a good idea. So it actually was put on a barge. The barge went along the Atlantic Ocean, then around Florida, came here, went into, I think, Mississippi, and was brought upstream finally, and only in the final few kilometers it was brought out, and then on the road it came to Fermilab. So the magnet somehow was used without chain. Okay. So what are the implications of what we saw? So firstly, of course, if true, then this very small effect, which happens at whatever, depending on where you start counting. Some people start counting at 2, where you say 2.002. Sometimes you're not counting at the after the 2 in G minus 2. So depending on that, you may say it's 6th decimal place or 9th decimal place. If true, this will be due to some interaction of virtual particles that we do not know, and therefore could be an interaction indication of new particles or new forces of nature, because that's going to change the calculation of the Feynman time. If this is true, you can have exciting hidden information about the vacuum, so to say, or new particles. However, there are caveats. Can this be due to some error in calculations? Because calculations are actually extremely hard and time consuming, even with high performance computers. And I will show you the discrepancies even among theorists who calculate this. On the experimental side, the same magnet was used in both experiments. So the question is, could there be some experimental error which was common between Dighe 1 and Fermi-Lab? And then the fact that you measured the same, in some sense, incorrect figure may have to do with the magnet. Okay, so we need to check it by independent means too. This is theory. The problematic calculation, as some of you did point out, is when hadronic contribution comes into play. Okay, so hadronic contribution can come in this triangular diagram like this, in the vertex, or it can come when modifying the photon form factor. Now, these are called as hadron vacuum polarization diagrams, or hadron, maybe it's HVP, I forget. Okay, the diagram. And calculation of this by perturbative means entirely is not possible. So people do use two ways. One is what they call as the Fano way. And by Fano way, it means they look at processes where a similar diagram contributes. So for example, pion-pion scattering and so on. This is the Fano way. The second way, so in Fano way, input is taken from experiments, and therefore as scattering experiment give you newer results, your answer will change, right? The second way is the lattice way, where things are done ab initio, because after all, this is long-distance contribution, this is non-perturbative, and you actually can do this calculation. This figure that you see gives you the current status of different measurements, of different calculations. So this band that you see is the experimental band. This is no theory in it. This is the combined result that you see right now. If you look at this reddish data points on the left, which are small error bars, these are the errors, these are the major calculations of in quotes Fano people, or the Fano way of doing things. This small blue thing that you see right at the bottom is sort of the average of all these Fano calculations done by what is called as the muon G-2 theory initiative. So people who did all these calculations actually came together and tried some matching among themselves and came up with this final error bar, which was a result in the so-called white paper of 2020. Now, as opposed to these, which look very far away from the experimental measurements, you have got a whole lot of calculations that are done by lattice calculations. As you notice, many of them actually have large error bars, so they overlap both the Fano calculations as well as the experimental measurements. One, which is called BMW 2020, which is the second from the top, you see it has quite a small error bar, and in that sense, it actually is inconsistent with all the earlier Fano measurements. So this is a big problem. It is recognized by the community of people who calculate this. So lattice calculations right now, the latest one, are inconsistent with this. So it is urgent to settle this theoretical issue, and this is the sort of major elephant in the room, so to say, caveat from the left-hand side, from the theoretical side, where one, before trying to claim that you have found new physics. From the experimental side, there are two upcoming experiments which do the measurement in a very, very different way, and that will be able to resolve this doubt about magnet being the common source of systematic error. One of them is an experiment that's going to happen, take place in Japan, in J-Park. It's called a J-Park G-2 or EDM experiment. It's again a similar, well, principle is similar. You look at muon. This muon goes around in a circle and it decays to a positron. The difference is this. Firstly, this storage ring is very small. Earlier was 7 meters. This is only has about 30 centimeters of radius. So it's very compact storage ring. Magnetic field is 3 Tesla, which is twice the one that we have currently. And therefore, even the particles go around in a more tight circle. Okay? So this is more controllable. And of course, this also means that energy cannot be magic, not 3 GeV, but 300 MeV. But this means that this V cross E term will still exist, but the flux can be much larger. And they don't simply have a single detector for measuring positrons, but what you see in this are sort of radially arranged detectors. So these are strips, and you can track the positron completely as it is going down. Okay? So the hope is that this measurement will be one check of what was the variation. Second method is a completely different method. This is being tried at CERN in a project called as muon E. This is an experiment of scattering of muons on electrons. So what you have are a lot of detector modules where muons, a muon beam of about 150 GeV, large energy beam, scatters across electrons. You observe these electrons and muons after their scattering. This is you can accurately go back and figure out where the vertex was. As a result, you measure the differential cross section of muon to electron to very, very great precision. And the hope is that with this, you will be able to figure out how the muon has precessed during its motion along this path. So hopefully in the next decade or so, you will be able to learn something. Okay, so just some concluding remarks. If you haven't got this so far, this is of course the message. Anomalous magnetic moment G-2 is definitely non-zero. Okay, QFT tells us this, and experiments have confirmed it for more than half a century. So there is no doubt about this. What is being measured is, in some sense, the anomaly of the anomaly. Anomaly in the anomalous magnetic moment. So this anomaly, G-2, has been measured to be different from the prediction at the ppm level or parts per million level. If this is true, it comes from new interactions or new virtual particles, and that's why people who look at physics beyond a standard model of particle physics are excited about this. But of course, muon is sort of a simple elementary particle, and the fact that an accurate measurement of its properties can tell us something about particles whose masses can be much, much larger than what we can see in LHC, for example, is something true. So I will end by saying that sometimes new discovery is simply a decimal place away. So I will stop here. Thank you. I can take questions.
Thank you, Amol. That was a wonderfully nice and very lucid presentation. Thank you very much. And I request all the members in the audience to please unmute themselves and just give a warm round of applause. Thank you. Thank you, everyone. So the floor is again open for more questions. There are some questions on the chat. I will take them one by one. So if there are any pressing questions from the audience right now, they can unmute themselves and ask.
Jyotishman, I'm Govinda again.
Yes.
Amal, this is just previous page when you said the CERN experiment. So this kind of experiment was not happened earlier. Just muon goes through an instrument and see the scattering. What is the speciality of this experiment?
So, okay, again, no, you are perhaps a better judge of this, but let me tell you my impression as a theorist. This is a precision experiment. You really need to know things quite precisely here. I do not know that this experiment was done anytime earlier. So the concept is simple, but the accuracy of measurement that is needed for the differential cross section of mu to V scattering is quite high. So you can imagine that this differential cross section would have maybe some particular shape, and you would need to measure it again at the top of my head to 1 part in the billion, right? So the coefficients of I don't know how many terms it will have. I just randomly say maybe up to cosine to the power 4 theta, for example. You have to determine the coefficient of cosine to the power 4 theta to the 1 part in 10 power 6. I do not know of any other experiment which was planned to do this, because this experiment doesn't seem to have any other use, so to say. I could not think of any other direct use of this, but maybe I'm sure audience has many people who are much better at this and more expert than me in understanding this.
Okay, no, so now my actually the main point was this is this muon, the atomic electron, it will scatter. So when it come to the atom, then this the effect of this atom on nucleus, is there any effect? How much that effect
So
will?
one comment I can make is now here, so as compared to earlier experiments, so the Fermilab experiment has 3 GeV muons. The JPAC experiment had 300 MeV muons. Here the energy is quite large. So it's quite possible, again, no, my guess as a night theorist, that the atomic changes may not matter much because this is a 150 GeV muon. But again, I do not know.
Okay.
The
Okay.
point,
Thanks.
Amol, is the point here is that unlike JPark or the Formula G-2 experiment, where you are directly accessing the G-2, this is an indirect way of, that is the way I would understand. This is an indirect way of saying that in case the muon has this anomalous thing, that how it will impact the differential cross section, isn't it?
Yes. Yeah. So it's like this, no? So similarly like this. Let's say the muon always was, the spin of muon was always pointing towards right. Then you would get a certain angular distribution. Okay? Now suppose the direction of muon spin changes slightly, the angular distribution will rotate. Okay? And so on and so forth. So as the muon spin keeps on precessing, the angular distribution in some sense keeps on rotating about its axis. This happens as a function of time, and that's what you measure. So very clearly, this is a very ambitious project. I don't know. So I'll leave it to you guys to figure out how feasible it is and so on. But if I understand correctly, already test beam runs have happened in CERN for muon E. I think the first test beam run has taken place.
Amol,
Yeah.
this is Acharya. Amol.
Yes, I can hear you.
Yeah. Okay. This CERN experiment, that beam is, it can be mu plus or mu minus also. Unlike in the Fermilab experiment or JPAR, it is the beam is mu plus, right?
Fermilab was definitely mu plus.
Yeah.
I think JPAC also is mu plus. My suspicion is here they will perhaps have a mu minus beam, because mu minus electron scattering would be cleaner for determining cross section, I guess. But I'm not sure. I'm not sure of what charge they use for this beam.
Could I make a comment?
Yeah, TPS.
Yeah, it's a little indirect, more having to do with it's a comment about gravitation and black holes, which people may find interesting. You may already know this. And that is, if we consider charged and rotating black holes which have an electric charge and angular momentum, I can once again go and calculate the gyromagnetic ratio G for such a black hole. And interestingly, it turns out that black holes, unlike other classical objects, have G equals 2, which makes the black hole more like an electron and less like a classical current carrying wire. And for many people, this is a very profound issue. Is there some way in which black holes, know about elementary particles? And there have been some very interesting discussions. I thought this may be of interest to people. Thank you.
Thanks. Yeah, I mean, wasn't aware of this. I think I'll perhaps go read something more about
Yeah,
this.
for me, this is a very interesting question. I've spent quite some time on understanding why it might be like this. Thank you.
Thank you,
But
Tim.
Amol, do you think there is a discrepancy between theory and experiment, or you would take the lattice calculation seriously and still wait? Uh,
I'm a conservative person normally.
Acha. Mhm.
So I will wait before jumping with this, but I will definitely keep an eye on this. I think it's worth doing the experiments, and it is worth improving this calculation, because you notice the lattice errors have suddenly decreased a lot in the last 1 year. If you look at
And in the wrong sort of way, it's worrisome.
yeah. So, but as I said, I'm not the person who can comment on the correctness or not of the calculations or the decrease in errors. There are people who are so this, for example, the G minus 2 initiative people, the averaging that they took, just to mention, wasn't only the fellow result but also the earlier lattice results. They did not include the BMW 2020 result, which actually came after the averaging one. In fact, this result came out on well, it was published on the same day that the experimental result came out. But perhaps there is some lattice person in the audience who might comment. I don't see exactly who's in the audience.
But interestingly, the experimental result has stayed steady.
Okay. Amol, what do you want?
Theory which has a problem.
Nilmani is here.
Yeah, but what do you want?
You want to comment on this lattice calculations giving different results?
Like how systematic they are, or why the error bar is small, or
yeah. So one question, of course, is what is it that they have done which has taken the error bar to small to this extent? And secondly, is there something that maybe the lattice community may be more aware of whether people have checked the calculations, whether there are some extra systematic that are not included in this error bars and so on. If you have
so
any
this
comment?
calculation has taken care of most of the uncertainties that other people have not taken care of, and also they have systematically addressed most of the calculations. Most of the systematic errors. Having said that, I mean, this is like you have seen the number is 10 to the minus 11, and to get such a small number from the lattice is not very like trivial. So I think more other groups need to do the same calculation, and many other groups are doing. So hopefully, in let's say in 5 year times, it will be settled. But this group actually did like an outstanding work for these calculations. They have addressed almost all the uncertainty related to this calculation.
Which group?
Only
BMW or
one
other?
of them, BMW. Only one problem they haven't put the they have still using the quenched strong like background field, like magnetic field still on the background, the QCD QED effect. But that uncertainty probably will not matter that much. But other than that, they have actually addressed all the uncertainties very thoroughly. So more people actually are looking for this calculation and will do it in that.
So Nilmani and Amol, if the BMW result is correct, then will we conclude that there is no discrepancy between theory and experiment?
small
Chemistry has no difficulty.
uncertainty, small, I think 1 sigma is like that.
MW is consistent almost. So,
Okay.
Yeah, I think still there is 1 sigma like
sigma is
that.
not difficult.
Yes. Okay.
Okay. Okay. So now there were one question by Manjeet from the audience that in the chat box is saying, if Manjeet is there, Manjeet, are you there? Could you unmute yourself? Manjeet? Oh, I'll read out the question. Okay. In simple language, is the anomaly in the magnetic moment a result of entanglement of particle with fields? The main point is in which particle one should look for. In this case, it is muon, something like that he has written.
Yeah, I can actually read that. So my answer would be, so the word entanglement, at least the way I use it, has a very precise meaning. And it talks about coherence between objects being maintained over long distances, for example. This is not exactly the case here. I mean, it is true that there is, it's an interaction of particles with fields. I will not call it entanglement. So what is happening does not fit with my narrow definition of the word entanglement. I would say it's interaction of particles with the fields, not entanglement.
Okay. Thank you, Amol. There is one question.
Amol, I have a question.
Yeah.
Hello?
Yeah.
Is there any experiment proposed with tau, because it scales with the mass? No, I mean, anomaly of the anomalous magnetic moment will be more. So, is there any experiment for tau?
So actually, well, the answer is, of course, I do not know. I don't know. I am not aware of any experiment being proposed. I haven't thought about what may be experimental problems with.
The problem is simple,
Decay lifetime. Lifetime is the problem. Unless you have very highly energetic tau beam, which will dilate, increase the lifetime in the lab, it will be permanent.
It's like thinking of a tau collider, right?
Yeah. So remember, if you want to increase the time for which you see tau, you increase the energy. Okay. When you increase the energy, you have to increase your radius. And that means that you will really need a very, very huge radius of the cyclotron in which you are going to make this particle.
But Amol, didn't you say that the energy is kind of fixed in order to cancel the third term?
Yes, and that works well for muon. Right?
So for tau, that should not be an issue.
We have to calculate. See, this A mu should be equal to 1 over gamma square plus 1. So for tau, of course, gamma will change.
But I mean, that should not be, I mean, it will be similar expression, or the gamma will change.
Yeah, true. Yeah. Okay, wonderful. So if you want to do, okay, let me give an answer which is hopefully correct. Okay, so since A mu is approximately expected to be similar, at least to first couple of decimal places between mu and tau, it means that gamma has to be similar. So magic energy would be the same. And if magic energy is 3 GeV, then you cannot have tau lasting for a long time. So
no, but why do you have to put in the magic energy like the JPRAC experiment?
Yeah, that's true. You don't need magic energy. That's correct. So what you need is long-lasting tau. Long-lasting tau would mean more energy.
I thought magic energy is making the expression simpler.
More energy would mean more radius, no? So you have to make something circle which is maybe hundreds of meters in radius. So that makes sense.
Yeah.
And then you have to make a magnet which is accurate enough for that distance. So one of the reasons that JPAC people made a compact object is because instead of making a magnet which had a uniform magnetic field over 15 meters of diameter, now they have to make uniform magnet over 60 centimeters of diameter. So for uniform magnetic field, having a very compact magnet is very useful. So that may be one negative point for tau.
Okay. Okay, thank you. Okay, I will take a question from. Oh, wait, could I just finish this? I will take a question from YouTube.
No, I'm just saying that this continuation of this tau production rate also will be very, very less. Pion decay, so tau, to get the tau also, that will also very difficult.
Yeah, source of pion tau, of course, will be, but
okay.
Okay. Thank you. So the question from YouTube is by Abhinav Chaudhary. He says, do muons interact with a quantum foam of subatomic particles popping in and out of existence while circulating in the muon G-2 magnet?
In fact, they do. They do it everywhere. That's the idea. Any particle which is moving always interacts with this, whatever you call quantum foam. I think that also the particular meaning. But no, with quantum fields that are always around. So it does interact. That's the reason it has this G-2.
Okay. Okay. Thank you. Yes, TP has a question.
Yeah, thank you. So Amol, the other experiment which was, as you know, in the news recently, what possible via BSM physics was this B-meson decay into muon and electron channel and possible violation of lepton universality. What is the current status of that experiment? And do these two experiments and the possible theoretical implications inform each other in any way?
Okay, so anomaly observed in the B-meson decay experiment, it's called as the RK anomaly, which directs to lepton flavor universality violation. It stands. It is more than 3 sigma. It's I think about 4 sigma now. We of course do not know resolution of that. There have been lots of papers on the archive and in paper which try to even satisfy RK anomaly and G-2 at the same time. But it's like a game. No? You can construct models. I think it's a good intellectual exercise to have. Some of these attempts might also even be useful because it's quite possible that the same new physics might actually give rise to both anomalies, in which case
okay.
right?
It will be great. Yes, yes.
Because in some sense, this is also lepton flavor universality violating, right? The magnetic moment of muon is different from magnetic moment of electron. So there is a violation of flavor universality here. So it's quite possible that they are connected, and people have tried. I cannot even count the number of papers that have tried to do this.
Okay, thank you.
Okay, thank you. Thank you, Amol. I don't see any other hands at this point. Any other parting comments or discussion points that anybody wants to mention? I see unmuted mic from Shrirupda. Shrirupda, are you unmuted for a question or?
Well, not really, but I could make a comment which is nothing really to do with muon G-2. But at the beginning of the colloquium, we talked about the electron spin and the concept of spin discovered by Uhlenbeck and Gaudsmit. Just like to remind you that actually the idea of spin had been found a year earlier by S.N. Bose. It was incorporated into his famous formula. And unfortunately, Einstein shot it down and changed it to polarization, which is why we don't have any evidence for it. But this has been mentioned by C.V. Raman and others also who have talked to Bose. Just a small point.
Okay. Thank you. That was nice. That was nice. Thank you. Okay. That was very nice. Thank you very much, Amol. That talk was, the starting point at least was very lucid for even a chemist like me. And it really transitioned into the actual issues of the explanation with the standard model. And of course, the experimental part was also explained very well. So thank you. And for this very, very important colloquium. And I am sure there will be more discussion in the community spurred by this talk and also by the work that has come out in April 2021. So thank you very much. I would like to thank the people managing the lecture theatre for putting this up for everyone also. Just an announcement, any of you can actually sit down in AG66 and listen to the talk in the big screen if you do not want to hear it in your local Zoom hardware. But I would like to also mention to everybody here that next week we have Professor Sanjay Vategaonkar from DCS. giving his sort of the colloquium, that is sort of the covering the work that he has done in TIFR, investigations of novel hydrogen bonds. That will be his title. Please join us for his sort of the final talk in the capacity at TIFR. So thank you very much, all of you, for joining in. I'd like to close this session. A big round of applause for Amol. Thank you. Thank you, Amol.
Right.